The Webb telescope is designed to see as far back in time as we can possibly see luminous objects, when the universe was maybe 100 million years old.
Just when we thought we had a solid understanding of the universe's beginnings, the James Webb Space Telescope has thrown us a cosmic curveball. In a shocking turn of events, the JWST's latest discovery challenges everything we thought we knew about the Big Bang. What secrets does deep space hold? What happened before the universe began? We have the answers now, so join us in today's video as we take a journey through the JWST's groundbreaking discovery of what happened before the Big Bang. You may think you know the Big Bang, but recent discoveries by the JWST have unearthed secrets about what happened before it. To fully understand these findings, we need to take a step back and delve into what the Big Bang is and how it brought us to where we are today. The theory suggests that the universe began as a tiny dense point of energy that expanded rapidly, creating the conditions for the formation of galaxies, stars, and more. Evidence to support this theory includes Hubble's law, which explains why distant galaxies are moving away from us. But that's just the beginning. The cosmic microwave background radiation, the abundance of primordial elements, and the evolution and distribution of galaxies have all given us clues about the early universe. But what really happened before the Big Bang? It's a question that has puzzled cosmologists for decades, and one that may hold the key to understanding the origins of the universe. While the Big Bang theory explains how the universe began, it doesn't account for what caused it or what came before it. However, there are several fascinating and plausible explanations that scientists have put forward to try to answer this perplexing question. One such theory is the Big Bounce, which proposes that the universe is part of an endless cyclical process in which a prior universe collapsed into a singularity and then rebounded into a new one. This idea has gained traction in recent years, and it's thought that the Big Bounce may be caused by quantum processes, gravity, or other spatial dimensions. Another intriguing explanation is the ekpyrotic scenario, which suggests that our universe arose from the collision of two branes in a higher dimensional space. This collision caused a rapid expansion known as inflation, which smoothed out the initial conditions of the universe. The branes may continue to collide, creating multiple universes in the process. Yet another theory is the pre-Big Bang scenario, which proposes that our universe developed from a condition of low energy and high curvature into a state of high energy and low curvature. This transition included a period of superinflation that magnified quantum fluctuations, creating seeds for the structures we observe today. And finally, there's the no-boundary proposal, which suggests that the universe has no boundaries in space or time, and that the Big Bang was simply a smooth zone when the universe's size became very small. According to this theory, the beginning of the cosmos was a quantum fluctuation from nothingness, determined by a wave function that encoded all potential histories of the universe. Furthermore, the universe's growth and development have long been a key of focus of scientific inquiry, and the JWST has recently made a groundbreaking discovery, the earliest proto-galaxy cluster ever found, just 650 million years after the Big Bang. As the universe formed, it went through a hierarchical process, starting with a nearly uniform distribution of matter and energy. However, cosmic inflation caused small perturbations that eventually led to the formation of peaks and valleys in density, as seen in the cosmic microwave background radiation. Gravity then played a crucial role in shaping the universe's structure, but its effects were limited by the speed of light. Overdense regions attracted nearby matter and gradually collapsed, eventually forming bound objects on a grand scale, while molecular clouds collapsed on a smaller scale, giving rise to the first stars and star clusters. And the earliest overdense regions were able to collapse in just 50 to 100 million years, giving us a glimpse into the universe's earliest days. Now, when stars are born, they create chaotic environments filled with radiation and winds, making it nearly impossible to predict their exact structure. These early clumps of mass draw in everything around them, merging together to form the universe's first massive galaxies. Some of these galaxies have already been discovered, with many of them being huge, rich in heavy elements, and constantly forming new stars. But there's still hope for JWST to find even earlier galaxies and stars. However, when it comes to the creation of galaxy clusters, the physics gets a lot simpler. The formation of these clusters is mainly determined by just three factors: the universe's expansion rate, the initial overdensity on the relevant cosmic scale, and the rate of gravitational growth over time. All that messy gastrophysics inside a galaxy doesn't matter for galaxy cluster formation, only gravity holds the key. And before the powerful JWST, there were various ways to uncover the grandeur of galaxies throughout cosmic history. One of the easiest ways was to look for large groups of galaxies in the same field of view, with similar redshifts, but with differing velocities. Galaxies within a cluster were zipping around at lightning-fast speeds relative to each other, sometimes moving several thousand kilometers per second. By using this method, astronomers were able to identify nearby galaxy clusters, like the famous Coma and Virgo clusters. Another method was to search for galaxy clusters that were heated up due to intense processes like the collision of gas clouds or star formation, which emitted X-rays that could be detected with the right equipment. These X-ray emitting clusters not only helped identify them, but also provided valuable information about their masses, gas contents, and merger histories. And finally, we come to the grand reveal of how galaxy clusters have been uncovered through the effects of their collective gravity, manifested in strong and weak gravitational lensing. When we observe a massive galaxy cluster, we can differentiate it from a set of isolated galaxies due to the lensing features created by intra-cluster matter, a mass that exists between the individual galaxies. For instance, CLJ1001 plus 0220 is a nearby mature galaxy cluster containing 17 distant galaxies, more than half of which are starburst galaxies, emitting light 2.7 billion years after the Big Bang. But galaxy clusters don't start off as fully formed objects. Rather, they evolve from an unformed state through a proto-cluster phase. Proto-clusters of galaxies are groups that haven't yet heated up their gas enough to emit X-rays, and they are the first examples of groups of galaxies in a comparable location in space. Using ground-based observatories like Subaru, Keck, and Gemini, scientists have identified two distant protoclusters, one containing 44 galaxies at a redshift of 5.7, corresponding to an age of 1.1 billion years after the Big Bang, and another consisting of 12 galaxies at a redshift of 6.6, corresponding to an age of 800 million years after the Big Bang. These protoclusters were found to be in the process of becoming gravitationally linked, and JWST's unparalleled cosmic vision is expected to break this cosmic record by stretching the earliest known cluster back to unimaginable times. Meanwhile, 3 surveys conducted by the JWST, JADES, GLASS, and SEERS have unveiled more insights into the Big Bang. SEERS identified 4 galaxies within a small area of the sky, all at the same distance of 4.9 redshift, corresponding to a protocluster that existed just 1.2 billion years after the Big Bang. However, within the GLASS field, which includes the magnifying effects of the foreground galaxy cluster Able 2744, the possibility of even deeper discoveries exist. And by sheer luck, 7 independent galaxies were detected within the same region, spectroscopically verified to be at the same redshift of 7.8, representing the earliest known protocluster of galaxies at a time of 650 million years after the Big Bang. The cluster's name, A2744Z7P90D, reflects its discovery in the lensing field of Able 2744 and its redshift of 7.9. This work reveals the most distant protocluster of galaxies in the universe to date and underscores the significance of detecting and validating all distant galaxy candidates for a single entity. Although some of the discovered galaxies were not linked to the protocluster, some candidates still lack spectra, emphasizing the importance of observing them. Researchers quantified the mass and velocity dispersion of the protocluster and made a fascinating discovery. The collective mass of 7 member galaxies is roughly equivalent to 400 million suns, nearly equivalent to the mass of the present Milky Way, setting a lower limit on the protocluster's mass. It should have expanded to at least 5,000 times its original size by now, or grown to the mass of the modern-day Coma cluster. Now prepare to be amazed, as the JWST has once again stunned the scientific community with its discovery of a diminutive early galaxy that packs a powerful star-forming punch. This discovery could be the key to unlocking the secrets of how the cosmic dark ages came to an end. Known as RxJ 2129Z95, the galaxy dates back to around 500 million years after the Big Bang and can be observed at a redshift of 9.51. This number indicates that we are seeing it as it existed a mere 510 million years after the birth of the universe. Despite its immense distance, the galaxy's faint light was boosted by the gravitational lensing effect of a massive foreground galaxy cluster called RxJ 2129.6 plus 0005. The 150 trillion solar mass cluster magnified and split the light of RxJ 2129Z95 into 3 images. JWST's near-spec instrument confirmed the galaxy's redshift and revealed strong emissions from high hydrogen and oxygen gas clouds within RxJ 2129Z95. Spectroscopic analysis of the galaxy's emissions lines revealed some of its exceptional features. RxJ 2129Z95 may be tiny, but it sure packs a punch. This early galaxy is only 105.6 light-years across, which is minuscule compared to our massive Milky Way galaxy spanning 100,000 light-years. However, despite its size, RxJ 2129Z95 has the same star formation rate as our galaxy, making it a powerhouse of activity. The JWST is uncovering that high star formation rates are common among galaxies in the early universe, but RxJ 2129Z95 stands out even among them. Its radius is at least 3 times smaller than other galaxies, meaning that an enormous amount of star formation is squeezed into a tiny volume. This discovery supports the hypothesis of hierarchical galaxy formation, where smaller galaxies form first and then merge to create larger ones. Intriguingly, there is no evidence of an active supermassive black hole at the center of RxJ 2129Z95, which could be significant in understanding the end of the cosmic dark ages. During this period, radiation ionized much of the neutral hydrogen gas in the universe, and the cause of this event remains a mystery. Was it radiation from black holes or bursts of star formation? The lack of a visible black hole in RxJ 2129Z95 suggests that radiation from bright young stars may be the primary source that brought the dark ages to an end. However, the amount of ionizing radiation produced by the galaxy needs to be measured to confirm this theory. If there are more similar galaxies out there, then they could play a crucial role in the ionizing photon budget. To learn more observations of galaxies at similar redshifts are needed, and with the JWST already confirming several very high redshift luminous galaxies, astronomers are sure to have a lot more to discover soon.